Hello, my name is Rachel, and today I will be talking about how mermaids fill the gaps in seismic tomography. But first, I'd like to give a brief introduction on seismic tomography. It's similar to medical imaging, just as doctors like to image the human body, geophysicists like to image the Earth using seismic data. With seismic data, we can create tomography models like this one here, which highlight the different structures of the Earth and help us understand complex processes. I'm specifically focusing on global tomography, which means I'll be using earthquake data. Earthquakes generally occur along the plate tectonic boundaries, as shown in this image here, and the data is recorded by seismic stations at different locations, like in this image. So in order to gain as much information as possible from the earthquake, we would like to cover the entire Earth with seismic stations. However, ocean bottom seismometers are expensive and difficult to maintain. Therefore, this is an unrealistic option. And so this is why we need to start investigating emerging data from new technologies, such as mermaids. In this project, we investigate if mermaid data can be used to improve global tomography and to help us better understand the interior of the Earth. Next, I'll talk about mermaids and the goals of this project. I'll compare mermaids with broadband seismometers and show some synthetic experiments. Then I'll discuss future goals. So mermaids are basically these robots that float in the ocean and continuously record acoustic data. This means it can record all sorts of stuff like a fish swimming by or a storm happening at the surface and even an earthquake, which is what we're interested in. When a mermaid records an earthquake, it floats to the surface where the location is immediately recorded and the data is sent out for processing. However, there are some challenges in this system. There's a location uncertainty due to the ocean currents. Because as the earthquake floats to the surface, the ocean can carry it to a different location from where it originally recorded the earthquake signal. So this can cause some complications. And mermaids also record pressure, which is different from normal seismometers. And mermaids record oceanic reverberations, which make the data extremely noisy and almost impossible to use. As for goals of this project, first we want to compare mermaid data from the South Pacific Ocean with nearby seismometers. So in this image here, I've shown the location of mermaids in the South Pacific, as well as seismometers locations. So mermaids were deployed in the South Pacific because it is home to one of the two super plumes that exist in this Earth. I've included this nice tomography model of the super plume as well as a cartoon to help you guys out. So basically, super plumes occur when large amounts of the Earth's mantle move to the surface. Since there are hardly any seismic stations in the South Pacific Ocean, it is difficult to image and understand the super plume. So we're hoping that mermaids can help with this. So next we generate synthetic experiments to better understand oceanic reverberations and to see how much we can suppress them from the original earthquake signal. Once we create a filter that works on the synthetic data, we can apply it to the mermaid data and investigate the use of mermaids in seismic tomography. So moving into the comparison, we focus on one earthquake specifically that occurred near the Peru-Ecuador border in South America, which is right here. I've also found 4 broadband seismometer stations located here, and they're located near the mermaids. And so here I'm demonstrating what we normally do in seismic tomography with the data. So typically we filter the data to long period bands. In this case, I'm using 40 to 100 seconds to reveal different parts of the seismic wave. And so long periods just mean longer wavelengths. And I've also labeled the P and S wave arrivals for the data right here and here. So in this slide, we're comparing mermaid data with data from a seismometer. And so this data looks very different from the data in the previous slide because of the way we filtered due to the mermaids. And so mermaids can only record shorter wavelengths. So that means we have to filter the data to that. So as you can see, this makes the data a lot more complex. And so I've labeled the P and S arrivals for the seismometer, and I've only labeled the P wave arrival for the MERMAID. And so this is because the complexity and the complexity of the signal and the oceanic reverberations make it hard for us to actually locate the S wave. And and for this reason, we're primarily going to focus on the P wave. And so there's also a difference in the type of measurements that are being used here. The MERMAID is measured in pressure, and the seismometer is measured with displacement. So we're actually working on a conversion right now, so we can directly compare these two signals and see the effects of the oceanic reverberations. So since we're focusing on the P wave arrival, one approach is to use this data. In order to use this data in seismic tomography, we can pick the first arrival time of the P wave, which I've shown in this image here, this black line. However, we actually want to expand on this idea and find the full first arrival P waveform, which would give us more information to use in seismic tomography. And in order to do this, we need to filter the oceanic reverberations. So I've created synthetic experiments to help visualize and understand oceanic reverberations. This model is a purely homogeneous ocean layer, which demonstrates simple oceanic reverberations. So we see the first reflection off of the ocean bottom, and then the reflection off of the ocean surface, and in a little bit. Okay, and now we can see multiples in the ocean column, which are the reverberations, and these are what we want to filter. And so we plan to actually test our filter on this simple model first. Okay, and so here I've actually created a more complex model where I have 7 different velocity layers, and the layers of the ocean are based off of this velocity model here. And so we implement a sound speed minimum in the second layer here of the ocean. And then as for the oceanic crust, we use just basic velocities for the oceanic crust. And then once we get to the bottom, we actually implement a mantle half space. Okay, and so here is what this experiment looks like. So you can see tons of reflections already. And it gets pretty complex. One interesting thing is that the ocean actually has a lot lower sound speed than the oceanic crust. So you can see that it's traveling slower in the ocean than in the crust. And now we're getting a reflection from the sound speed minimum. And then we'll get a reflection from the ocean surface. And we're getting our first reflection off of the ocean bottom. And so, yeah, you can see how complex it can get. And so here are the synthetic waveforms that I generated from my complex experiment. And so our goal is to filter this data so we can extract the information for seismic tomography. Okay, next we are going to design a filter that acts similar to this cartoon here that I've shown. And basically we have our output, which is the data recorded by the MERMAIDS. And there is an input present in that output signal. And so this input is the original wave field with no reverberations present. So we actually want to extract this input from the output. So once we've done that, then we can utilize the MERMAID data and hopefully construct a more accurate global mantle model to better understand the structure and processes of the Earth, such as the Pacific superplume. So here are my references, and thank you for listening.